increased. So also we say this is soft starting. It's also we say this soft starting method because there are a large number of every value you can get you can adjust the voltage. You can get any voltage value. So this is method. This method is good. So this is by the reducing voltage. Reducing voltage. Also, this voltage is state voltage. This voltage is state voltage. First, the method 1 auto transformer. The method 2 star data, and the method 3 is the soft starting controller. So there are 3 methods of reducing voltage. So these three methods generally are based on the squirrel cage machine. And next we'll see another method. Generally, it usually is the rotor is the wound rotor. So we call this is the increasing rotor resistance. So by this this can adjust the resistance. So this is the state. This is the rotor. This is the rotor winding. This is the rotor winding. Because this is the wound rotor. It's a wound rotor motor. So the state winding not joined in this big. We just increase the rotor resistance. It's external rotor resistance connected in series with the rotor. In series with the rotor. By increasing the rotor resistance, we can change the torque speed curve. We can change the torque speed curve. We have studied earlier. We have studied the curves earlier. Different resistances corresponding to different starting curves. So this method, we'll see the equation. This is this equation. This equation is the current, is the road current. We can calculation the road current. If the resistance is larger, okay, we have the anti resistance. So this is larger, and the current will decrease. So this is very good. The starting current will be reduced. But we see the torque. The torque is calculated with this equation. If the resistance by the sphere, we see the torque. We can see the different curves. The starting torque from this one to this one. So if we add the resistance, will have larger start torque. So the torque is also good. The maximum torque is unchanged. This curve, the maximum is here. In this curve, the maximum torque is here. In this situation, the maximum torque is here, corresponding to different speed, but the value, the torque value is the same. The torque value is the same. So use this method, we can decrease the current, but increase the starting torque. So this is a very good method. So they are so good, but what's the drawback? What's the drawback? What's the disadvantages? We see that we'll have losses. Power losses on the resistance. So when starting, starting, the efficiency, the motor efficiency will be a little lower. Okay. So this is for the wounded. Let's see that. So this method is for the wounded rotor induction. We can add external resistance to the rotor in series with. But if it is a squirrel cage, squirrel cage motor, we can't access the rotor circuit, so we can't add resistance to the rotor. So how to start it if we don't use the reducing voltage? We have some, we see here. We have another method. By designing the motor by a special method. You can also see this in the textbook. We call it the deep bar, or and this one the double cage. So this is the two methods. For a squirrel cage, we have no access to the rotor, but we have also changes the rotor resistance. How to change the rotor resistance? Just by this design, this special design. We know the current. Of the rotor. The frequency is different. Between the starting time and the normal running time. And starting time, the frequency of the rotor is high, but when the normal running, the frequency of the rotor is low. So different frequencies, we use this method. There's a skin effort in current. If we have learned the AC circuit, we know the skin effort. The current will tend to flow on the surface of the bar, with the smaller cross, response. So it have a high rotor resistance. high rotor resistance. But if the frequency is low, so the section is large, and the resistance when normally running, the resistance is small. So this is the reason. Different time have different resistance. Different time have different resistance. Just because the frequency of the rotor is different. Let's see this. So it's this square. So it is current for the different. You see this graph on the different eye. So thus we have a variable rotor resistance. Use a special design. The deep bar or the double special design to get different rotor resistance. So this method is special. This method is special. So we see this. We also know the four kinds of motor. We see the C and D. Especially D. Or usually it uses the deep bar, or the double cage mechanism. So the starting torque is different. The starting torque of the four kinds is different. So the D kind of the motor, it has the largest starting torque. So this is the special design. This is the special design method. Class A and Class B. Class A and Class B is the general method. It has low starting torque. C and D have high starting torque, because they have different designs. So there are time. Can this use the? Can see the video? Okay. Let's see some video about the induction or about the starting method. No one? So it's the auto transformer method. This one? Huh?
Subscribe and press the bell icon. Never miss an update.
The circuit diagram for the auto transformer starting off motor is shown. The auto transformer has tapping switches in the secondary winding. The tapping switches provides output voltages of 50%, 65%, 80% of the supply voltage. The motor is connected to the secondary winding of the auto transformer through the tapping switches during starting of motor. In the auto transformer starting circuit, there are three switches SW1, SW2 and SW3. To start the motor, keep the switch SW1 open. Close the switches SW2 and SW3. As soon as the switches are closed, the auto transformer supplies 50% of the supply voltage. The voltage supplied to the motor from the auto transformer is increased from 50%, 65% and then to 80% of supply voltage by switching the tappings. When the maximum voltage output is obtained from the auto transformer, the motor is switched to direct voltage supply. However, during changeover of supply from auto transformer to direct voltage supply, there may be transient current and torque. To avoid such transients, the transformer start point should be opened and the transformer will be no longer included in the circuit. Now, the switch SW3 is opened. The start point in auto transformer opens. Then, a small part of transformer winding will be in series with the motor, which gives series impedance to the motor. After a further time delay, SW2 is opened and SW1 is closed. The motor is directly connected to supply. Now the motor runs with rated speed with full supply voltage. Thus, you have understood about the function of auto transformer starting of three-phase induction motor.
In this media, you will learn about rotor resistance stator. This stator is used for starting the slip ring induction motor. Stator windings are connected across the three-phase supply voltage. The rotor windings are connected to the star-connected resistances through the slip rings. In slip ring induction motor, starting current is controlled by the external rotor resistances. Rated line voltage is applied to the stator circuit and the rotor resistance is reduced gradually to obtain the rated speed. A controlling resistance connected in rotor circuit adjusts the starting current. The rotor resistance is kept at maximum position while starting the motor. This allows a minimal current flow in the rotor and hence reducing the stator current. This is because stator current is proportional to rotor current. When motor gathers its rated speed, the external resistance is slowly reduced in steps. Then rotor windings are short-circuited at the slip rings. Thus, once the motor picks up rated speed, the resistance circuit is cut out from the motor. Thus, you have learnt about rotor resistance startup.
Track and model.
Hey there guys, Paul here from the Engineering Mindset Ions compared to the other phases. This means that the magnetic field will change the intensity. We have an electrical term. Here's a real world example of an induction motor's electrical term. We always connect the supply side to terminals U1, B1 and W1. Now for the motor to run, we need to complete the circuit. And there are two ways to do this. The first way is the delta configuration. For this, we connect across the terminals from U1 to W2, V1 to U2, and W1 to V2. This will give us our delta configuration. Now when we pass an AC current through the phases, we see that electricity flows from one phase into another as the direction of AC power reverses in each phase at a different time. That's why we have the terminals at different arrangements, because we can connect across and allow electricity to flow between the phases as the electrons reverse direction at different times. By the way, if you want to learn more about how three-phase electricity works, then we covered this in great detail in our previous videos. Do check those out, links in the video description down below. Now, the other way that we can connect the terminals is to use the star configuration. In this method, we connect between W2, U2 and V2 on only one side of the motor terminals. This will give us our star equivalent design. Now when we pass AC current through the coils, we see that the electrons are shared between the phases at the terminals. So looking again at this real world example of the motor terminals, can you tell me which method is being used? 3, 2, 1, correct, is the delta configuration. The two ways we just saw of configuring the motor in star or delta are fixed methods. To change them, we have to physically cut the power, open the motor terminals, and then rearrange them. Now this isn't exactly practical to do. So how can we automate this? To do this, we need to use some contactors. Now they come in various designs, but if we look inside one, the basic operation is just a switch that can either make or break a circuit to control the flow of electricity in all three phases simultaneously. So we take our main contactor, and then we connect our three-phase supply to one side, and then we connect the other side to the respective terminals within the induction motor's electrical terminal ones. We then take a second contactor, which will be used for our delta circuit, and we feed our three phases into this also. From here we connect our phase 1 to terminal V2, which is the phase 2 coil. Then we connect our phase 2 to terminal W2, which is the phase 3 coil. And finally, we connect our phase 3 wire to the U2 terminal, which is the phase 1 coil. Now we take another contactor, which will be used for our star circuit, and we connect our three-phase power into this. On the top, we just connect all three phases together. And just lubricating of the contactors so that we can see what's happening inside. Now we start in the star configuration, and to do that we activate both the main and the star contactor terminals so that they close to complete the circuit. Now when we pass electricity through the circuit, the electricity passes through each phase and coil, and then out through the motor terminals and into the star contactor where the path of the electrons is shared. This allows them to flow in and out of another phase as the direction of each phase changes. This star connection method will run for a few seconds before switching over to delta. For the delta connection, we disconnect the star contactor and then close the delta connection. This all happens very quickly. Now we have the electricity flowing in, but it splits direction. It flows into both the main as well as the delta contactor. The electricity in the main contactor path will flow into the motor coils, and the electricity which took the delta contactor route will flow to the opposite side of the motor terminal. Each will then flow between the different phases as they reverse direction. To control the changeover from star to delta contactors, we simply use a timer to control this. This will automatically change the configuration over after a set amount of time. Additionally, there are more advanced versions which will monitor the amps or motor speed. If you are in the US, then you might find these colors being used. This is for a 208 volt 3-phase supply, but the colors will be different if you're using a 480 volt 3-phase supply. In the UK, EU and Australia, you'll find these colors used for the phases.
Yes,
If you're in the UK, then you're probably still going to come across versions of the red, yellow, blue colors being used. This is an old, outdated color system, but old installations are still going to exist. So coming back to this real-world photo of a star delta starter, can you tell me which part is which? 3, 2, 1? Correct. This is the main contactor, this is the delta contactor, this is the star contactor, and this is the timer. Notice on the star contactor, they've just connected 2 wires into the same terminal to create that star point. So why then do we use star delta starters? We use the star delta starter to reduce the inrush current when the motor starts. When a large induction motor starts in delta, their starting current can be over 5 times higher than the full load current which occurs when the motor stabilizes and runs normally. This huge surge in current will cause lots of problems. The building's electrical system will be hit by this sudden large demand. The electrical infrastructure will rapidly increase in temperature, leading to component failure and even electrical fires. The sudden large demand causes voltage drops throughout the building's electrical system. This can be visually seen because the lights will dip. This can cause many problems for sensitive equipment such as computers, servers and safety systems. So to reduce the starting current, we simply need to reduce the starting voltage. The star configuration will reduce the coil voltage to around 58% compared to the delta configuration. A lower voltage will lead to a lower current. Current in the coil while in star configuration will be around 33% of the delta configuration. This will also lead to a reduction in torque. The star configuration torque will also be around 33% compared to delta. So let's look at a simplified basic example of what's happening here to understand it further. Now let's say we have the motor connected in delta with a typical European supply voltage of 400 volts. That means when we use a multimeter to measure the voltage between any 2 phases, we will get a reading of 400 volts. We call this our line-to-line voltage. By the way, if you don't have a multimeter, then I highly recommend you get one for your toolkit. It's an essential piece of kit for any electrical fault finding and building your understanding of electricity. Links down below for which one to get and from where. Now if we measure across the 2 ends of the coil, we again measure the line-to-line voltage of 400 volts. Let's say each coil has a resistance or impedance, as this is AC power, of 20 ohms. That means we will get a current reading on the coil of 20 amps. We can calculate that from 400 volts divided by 20 ohms, it equals 20 amps. But the current in the line will be different. It will be 34.6 amps. And we get that from 20 amps divided by the square root of 3, which gives us 34.6 amps. That's because the phase is connected to the 2 coils. Now if we look at the star configuration, we again have a line-to-line voltage of 400 volts. We see that if we measure between any 2 phases. But with the star configuration, all our coils meet the star point or the neutral point. It's from this point that we can run the neutral line if we need to. So this time, when we measure the voltage across the ends of any coil, we get a lower value of 230 volts. That's because the coil isn't directly connected between 2 phases like the delta version was. One end is connected to the phase, but the other end is connected to the shared point, or the neutral point. So the voltage is therefore shared and will be less because one phase is always in reverse. We can see the 230 volt reading by dividing 400 volts by the square root of 3, which gives us 230 volts. As the voltage is less, the current will be 2. If the coil is again 20 ohms of resistance or impedance, then the current is calculated by 230 volts divided by 20 ohms, which is 11.5 amps. The line current in this design will also therefore be 11.5 amps. So we can see with the delta connection, the coil is exposed to the full 400 volts between 2 phases, but the star connection is only exposed to 230 volts between the phase and the neutral point. So we can see that the star uses less voltage and therefore less current compared to the delta version, and that is why we use it first. Okay guys, that's it for this video, but to continue your learning, then check out one of the videos on screen now, and I'll catch you there for the next lesson.
Okay. So this video is very good. Yes, sir. They don't understand real table. You can also to the WeChat, upload to the WeChat. It's visible on the, so it's from the YouTube. Yes, from the YouTube. So there are many good sources about motor on the YouTube. So YouTube is a good place, but in China, you know, most of us can't access the YouTube, the Facebook, the Twitter, can't access. Okay, class is finished.